In the next step, we want to understand how well does the model fit our data. The most common way to evaluate the overall fit of a linear model is by using a metric called the R-squared value. R-squared is the proportion of variance explained, meaning the proportion of variance in the observed data that is explained by the model, or the reduction in error over the null model. And the null model here just predicts the mean of the observed response, and thus it has an intercept and no slope. Don't worry if you're not very familiar with all these terms. We'll just go over how to interpret R-squared in a user-friendly way. R-squared is a metric that lies between 0 and 1, and the higher the R-squared, the better your model is, because it means that more variance is explained by the model. So here's an example of what R-squared looks like. You can see that the blue line explains some of the variance in the data. So R-squared there is 0.54. The green line, on the other hand, explains more variance. So it has more R-squared, 0.64. And finally, the red line fits the training data even better. So the R-squared there is 0.66. So the better the fit, the more the R-squared. That's how I want you to interpret this metric. So in our example, let us calculate the R-squared value. So all I have to do for stats models is pull out the R-squared attribute. And for scikit-learn, I just have to pull out the score, which is a function, and I again pass my x and y, and it gives me the R-squared values. Now, is that a good R-squared value? It's definitely hard to say. The threshold of a good R-squared value depends widely on the domain. Therefore, it's most useful as a tool for comparing different models. So you don't want to make a statement saying, okay, 0.8 as an R-squared is a good R-squared and 0.7 is not. But when you're really building multiple models for predicting the same variable, you have a comparison benchmark where you can compare these two models and actually select the better model out of the two.